Last time, we derived the equivalence between fluid and lattice gas and also the Ising model. And at the end of the lecture, we use a different alternative approach to establish such an equivalence, namely by going to directly the configuration sum from the fluid partition function to the partition function of a lattice gas. And then we continue this derivation today, and we consider the volume of the fluid to consist of the many unit cells with the radius a, and within each little cube or unit cell, we can have at most one particle populating there. Okay, so this is the same hardcore condition that we assumed last time previously, and we could just equal partition the whole volume in terms of this little unit cells, and we choose the unit cell with the size a, which is less than the hardcore radius. The product of this phase space integral now becomes the sum over all these little volumes of alpha unit cell, and the total number of cells is given by this ratio between the total volume and each unit cell volume. And as a result, we consider the interaction between all these molecules in the fluid equivalently the interaction between this unit cell, because within each unit cell there's only one particle in there. So the U2, the two-body interaction between the particles at site I and site J in the original fluid system now becomes the interaction between this unit cell alpha and beta, and we will make another simple approximation by considering just the nearest neighbor and no interaction beyond the nearest neighbor sites. So the fluid version of the two-body interaction between Ri and Rj now can be rewritten in terms of the, say, density-density interaction between this nearest neighbor unit cell. Same constraint for this total number of particles, namely when you sum over all this occupation of n alpha unit cell, and you get back to this total number of particles, which is the same as you sum over all bunch of delta function of a fluid system. So the n alpha is in general a function of the real space position, but we could assume that this is simply just within the unit cell. Then we go back to this partition function, especially when we sum over this Boltzmann weight of this potential term, and we call this Qn in the partition function, and we consider the Qn that unit cell configuration, but we could interchange the particles freely, so there's n factorial such of possible configurations that could be specified by this different particles at site I and site J. So then we put n factorial here in front, then we simply just use that approximation that we made, to rewrite this integrals of this phase space volume position vector, and in terms of this sum over all this unit cell. But we know that there is a constraint to be satisfied, namely when you sum over all occupation within the unit cell, you get a total number of particle n, and n goes to infinity in the thermodynamic limit. So therefore, this constraint summation denoted by sigma prime, where this prime refers to the sum or summation over the occupation subject to the constraint, meaning this constraint needs to be satisfied. So this is slightly different from the unconstrained summation. We need to really consider the constraint in the summation here, because that is the condition, hardcore condition over there, that we need to satisfy whenever we sum over n alpha. But we can get rid of this constraint by going to the ground canonical ensemble. This partition function for this ground canonical system is given by this factor that we introduced earlier. Remember, this Qn is just this Qn here. You can either represent this Qn in terms of this fluid language or the unit cell language. But we choose to represent Qn in terms of unit cell. And all this other factor here, for example, this chemical potential term, also this thermal wavelength, lambda t, appear in the previous version. Okay, so the only term that we need to take care is the constraint summation here. So you sum over all possible total number of particles from 0 to infinity, but inside the summation over little n alpha, this unit cell, but little n alpha summation would need to satisfy this constraint. But this kind of a product of the two summations could be further divided in terms of the many different terms. And when you sum over all these different terms, you get back to this unconstrained summation. So let me just explain. Suppose we have this kind of a double summation for any function f, which is the function of n alpha, and when you sum over n alpha to satisfy this constraint, we can simply just spell out, expand all possible sum for this little n alpha. Namely, we could just add all these different terms together, but with each term, you get one possible constraint. For example, this first term is the term which satisfies total sum for n alpha is actually 0, which is simply just capital N, total number of particles goes from 0 to 1 to 2 to 3, and so on to infinity. And so you simply just expand all these terms. So this is total number of particles being 0, and the second term is total number of particles being 1, and so on and so forth. And the final term is the term where you have infinite number of particles there. So when you sum over all possible terms with a constrained sum, and you can show that equivalent to this unconstrained summation, where you don't have such a constraint when you sum over this n alpha. So then we could just simply use that mathematical equivalence between the unconstrained sum and constrained sum. Okay, and as a result, we could just replace this double sum by the single sum where we don't have any constraint. And when we express this fluid partition function in terms of the unconstrained summation expressed here, then you could simply notice that this form, mathematical form of a partition function of a fluid, is identical to the partition function for lattice gas, because you could rewrite this term in terms of the Hamiltonian minus mu bar times total number of particle m, where mu bar is the equivalent chemical potential, which is the chemical potential of the physical parameters plus this shift, this d over beta times log a over this thermal wavelength. And the rest of the term is really identical to the lattice gas system. And we know from the previous lecture that there is equivalence between the lattice gas problem and the Ising model by a proper change of variables, and therefore we establish the equivalence between the continuous fluid and the Ising model through the lattice gas. So there are two types of equivalence in statistical mechanics that I mentioned earlier. One type is called exact mapping or exact equivalence. And in this case, we have an exact mapping between the lattice gas problem and the Ising model. But when we map this fluid to the lattice gas, we make approximations. Remember that the hard-code approximation, it is approximation that we made in order to argue that the fluid can be rewritten in terms of lattice gas. But from lattice gas, it is an exact mapping onto this Ising model. But oftentimes we say that there is equivalence between the fluid and the Ising model, but there's just a side remark that when we map the fluid onto the lattice gas, we made the hard-code approximation, which is reasonable approximation. But there's a second type of equivalence called approximate equivalence, namely these two partition functions between the system 1 and system 2 are not identical, but near this critical point, they behave the same way. Okay? Namely, they have the same critical exponents, and they have the same scaling function. They have all the same critical properties. So that is what I say here. The Z1 is not equal to Z2, but near this TC, Z1 is the same as Z2. I will give you more examples of this approximate equivalence later. But you can see from this derivation that the seemingly two different systems, namely the fluid and the Ising model, at least near the critical point, they behave exactly the same. And even we could rigorously map this lattice gas Hamiltonian onto the Ising model. So indeed, they are equivalent in many ways. Okay, so let's take a short break. When we come back, I will make some final remarks regarding the equivalence, the mapping, and the quantum mechanical effect on the finite temperature transition and so on. So let me just make some final remarks before we move on to the actual calculation of the Ising model. The first remark is the difference between the factors that we can determine in the phase diagram and the factors that affect the critical properties. In short, the phase diagram depends on much more factors than the factors that determine the critical properties. So let me explain. So usually the phase diagram, the thermodynamic quantities and correlation functions of many statistical many-body systems depend on the following four factors. One is the specific values of the coupling constant, which I call this Ki. So of course, depending on the value of the coupling constant, the system could be in either phase of the phase diagram. And number two is the symmetry of the models. Is it the discrete or continuous symmetric models? And what is the actual symmetry group that the system has? For example, is it the O3 rotational invariant model with the O3 symmetry, or it is a Z2 or Ising-like symmetry? Okay, so the symmetry group actually plays a crucial role. And number three is the types of the lattice. Is a square lattice, a triangle lattice, a cogomate lattice, and so on. And the dimensionality, whether this is a one-dimensional chain or a two-dimensional plane or a three-dimensional crystal structure, and so on. And finally, everything else that you can think of. So namely, the phase diagram and all these thermodynamic properties depend on many factors, the microscopic Hamiltonian and coupling constant and symmetry and lattice and everything. However, near this critical point of a statistical systems, physics depends on much small group of factors. So namely, there are only three factors that determine the critical properties. One is symmetry of the order parameters, as I mentioned earlier. And number two is the dimension of the lattice. Symmetry and dimensionality are the two very important factors. And finally, the nature of the critical points is some kind of continuous phase transition of the first order jump. What kind of the continuous phase transition do we have? Is it the magnetic kind of a phase transition or other types, a disorder phase transition? But near the critical point, physics does not depend on factors that determine the phase diagram. For example, it doesn't depend on the specific values of the coupling constant. And it doesn't depend on the exact model Hamiltonian that you have. As we explained just a moment ago, that near the critical point of a fluid and an Ising model, they behave the same. So only the symmetry and dimensionality and the nature of the critical point that determine the critical properties of an Ising model and fluid. Okay? But this kind of very fewer factors, nature of these critical properties can be justified by the renormalization group analysis that we will study later. Okay? By the RG argument, we could understand why those factors are not important. So it's called irrelevant factors. So some of these microscopic parameters, vectors, can determine this phase diagram, but they are irrelevant. They are not important when we talk about these critical properties near this transition. Okay, so that's a very important remark. And the final remark is the quantum effect. So some people may say that at finite temperatures of some kind of a quantum mechanical Hamiltonian, quantum mechanics certainly will jumping to affect these critical properties. But is it true? For example, the superconductivity and magnetic system, magnets, and so on. So quantum mechanics plays an important role at ground state. But the main message here I would like to tell you is that near the finite temperature transition, the quantum mechanics doesn't play an important role. So, but we need to answer this question. So why on Earth can a classical statistical mechanics describes all of this? So the key point is that the behaviors near the critical points at any finite temperature, quantum mechanics is not relevant. So this is the statement, but why is that so? So the reason why the quantum mechanics is irrelevant near the transition or near the critical point is that, remember, near the transition, the correlation length diverges. So all the thermodynamic properties is governed by the region of the size, which is approximately the correlation length. But the correlation length diverges at the transition, which is much larger than the typical quantum mechanical length scale. Namely, on the whole system, when it reaches to the critical temperature, then the correlation length C diverges there. And the divergence of this correlation length governs all the thermodynamic quantities and behaviors near the transition. And on the other hand, quantum mechanics only govern the length scale, which is much smaller than the correlation length, which diverges. Okay? And the fact that the correlation length diverges, remember, it is proportional to the distance to the, say, critical temperature to some power, and that is determined by this how close the system to the critical temperature, and it has nothing to do with quantum mechanics. In other words, quantum mechanics does affect the zero temperature properties determined T equals 0 physics, namely the ground state of the system, but usually the d-dimensional quantum mechanical problem is equivalent to E plus 1 dimension, the classical system. So we will make that link later, okay? But quantum mechanics enters only at zero temperature limit. It doesn't play a role at the finite temperature transition when the correlation length diverges, okay? So, and we will come back to this point later, and this explains why there are so many quantum mechanical problem systems where they have this finite temperature transition, but near the transition, the classical statistical mechanics can describe such quantum mechanical systems with a finite temperature transition. All right, so that's the basic reason why this classical statistical mechanics still works in order to describe such a finite temperature transition of a quantum mechanical systems. Okay, so let's take a short break. When we come back, we will formally calculate the partition function and the thermodynamics of Ising model. Turn to the new chapter, which we studied how phase transition occurred in practice. So as we realized and understand that how phase transition occurred in principle, but in practice, we need to really obtain and derive such a critical properties and phase transitions by directly computing this partition function of a simple toy model. And that simple toy model is our favorite Ising model in one dimension. So let me just start writing down this Hamiltonian of the Ising model in 1D in the presence of the magnetic field H. So for the later convenience, I define the dimensionless parameters little h, which is this capital H, the magnetic field, divided by kBt, which is the beta. I define the dimensionless coupling constant beta times j for its coupling constant of the Ising term. And the partition function could be expressed in terms of little h and capital K and the total number of spins, and in terms of this summing over all possible Boltzmann weights, that Ising Hamiltonian. And to illustrate this in graphics, we could just lattice points in one-dimensional spin chain, and there's a nearest neighbor ferromagnetic couplings between the spins on the neighboring sides. And we will later sum over this all the spin configurations of this Boltzmann weight and get the analytical form for the partition function. So, but to do so, we need to fix the boundary condition, because boundary condition may affect a little bit of our final results. So there are two ways to specify the boundary condition. One is there's no boundary condition at all. The spins are freely move at end of this chain. Okay, so called the free boundary conditions, and we study the simple case that there's no external field. So in such a case, this partition function for free boundary conditions is simply just this product of the summation over all individual spins from the first spin to the very last, and inside the summation, it is just the Ising coupling between this neighboring sides I and I plus 1 or I minus 1 and I. And to more conveniently make progress, we define a parameter eta, which is the product of these two Ising spins on neighboring sides, where I runs from 1 to n minus 1. And this eta I can take two values. One is plus 1, another is minus 1, depending on whether this Si is the same as Si plus 1 or with a minus sign relative to the neighboring spins. Okay? Because each of the spin on side I or I plus 1 can take either plus 1 minus 1. So plus 1 times plus 1 is actually plus 1, but plus 1 times minus 1 is actually minus 1. So eta I can take something like same Ising spin can take. So then this partition function is simply just sum over S1, but the remaining summation is replaced by sum over eta. And inside this partition function of a Boltzmann weight, we have this e to the k times eta 1 plus eta 2 plus eta n minus 1. So effectively, we could simply just redefine this product between the nearest neighbors Ising spin as some kind of a new variable, independent variable, eta I. But when we sum over, say, from the start, which is S1 plus times S2, which is eta 1, and eta 2 and eta 3 and so on. So previously, you sum over individual spin variables running from plus 1, minus 1, but effectively, you could rewrite this partition function in terms of summing over all these etas, because eta also takes plus 1, minus 1, depending on the relative signs of the neighboring spins. So these two expressions of partition functions are identical. But when we sum over individual spins from S1 to Sn, there's n summations. Okay? But in terms of eta, there's only n minus 1 eta variables because of this product nature of this two neighboring spins for a single eta on side I. So then when we sum over all this nearest neighbor product of the spins, and we just have this n minus 1 summation for etas. So we need to retain or keep the first sum over S1. In that case, we could say that these two summations are equivalent or identical. But the remaining, this summation of n minus 1s for the eta, we could actually see that this exponential factor here depends only on this eta 1, eta 2, up to eta n minus 1. It has nothing to do with this S1. Of course, this S1 is hidden in this eta 1, S1, S2. But now we consider this eta I as independent variables to be sum over. Remember that. So then this summation is simply just n minus 1 independent summation, and we simply just multiply this independent n minus 1 summations, and later we sum over this S1. But these independent summation over eta i's gives you just 2 coach k, right? Because each of these eta I runs can have only 2 possible values, plus or minus 1. When you sum over all possible values of eta, say eta 1, you get e to the k plus e to the minus k, which is 2 times coach of k. But you get n minus 1 such independent summations and multiply together, and therefore you get 2 times coach k altogether to the power of n minus 1. But you need also sum over independent spin on the first side S1, but the remaining part of the summation is independent of this S1, and therefore you get an overall prefactor 2 times 2 coach k to the power of n minus 1. So that's the first calculation based on the free bounding condition, namely at 2 endpoints of the spin chain, there's no constraint, no relation between the spins on the 2 sides of the chain. But there is a second bounding condition, which we call this periodic bounding condition, namely the spin on side, say, 1 is actually the same as the spin on side n plus 1. So it's kind of a periodic array of one-dimensional spin chain. So in other words, the variables for this first spin on site 1 is the same as the spin after n sites shifts. So from this boundary condition, which is periodic, the partition function is given by the same product of n spin summations and this Boltzmann weight, which is e to the k times sum over I runs from 1 to n minus 1, si plus 1 plus the n point summation, which is Sn times S1. So let us define the eta variables the same way that we defined for this free bounding condition. Namely, suppose we define this S1 to be eta 0, and eta 1 is actually what? S1, S2, and so on and so forth, n minus 1. So the states of systems are completely determined by all these etas, from eta 0 to eta n minus 1. So you can show that S1 times Sn, which is the interaction between first and the last. So in this periodic bounding condition, it is more convenient to actually use a circle or a ring to describe such a Ising chain on a ring. So this is S1 and this is Sn, and so on and so forth. This is n minus 1. So you can see that if I have one more sites after n spins, then this n plus 1 spin is the same as S1. So this is what we call this periodic boundary condition. But all the spins could be periodically displayed in a circle or a ring where we have nearest neighbor Ising couplings between S1 and S2 and so on, S2 and S3. But we have additionally one more coupling between the very first of the spin S1 and very last spin Sn. So there is an additional coupling here, S1, Sn. But if I add one more spin on the ring, you get the same spin configuration back to the first spin, S1. So it's kind of a periodic at boundaries, but this bounding condition is certainly different from this free bounding condition where you don't have any relation between S1 and Sn. So there's no talking between the very first and the very last of the spins in the chain. But you see later that these two different bounding conditions will give rise to slightly different partition functions, but in the thermodynamic limit, there's no difference. So they all merge into the same thermodynamic limit. Okay, but we need to be careful when we really compute the partition function at a finite system. So go back to this, the very last coupling between S1 and Sn. We can show that this product is actually the same as the product of all this eta 1, eta 2, up to, say, eta n minus 1. So to see this equivalence, you could actually use this identity that since on every site, Si takes only plus 1, minus 1, there's two possible values. If you square this Si on every side, you get 1, because either plus 1 times plus 1 is actually plus 1, or minus 1 times minus 1 is actually plus 1. So if you square this Si, you get 1. So you use that property, you can show that if you take a product of all these etas ranging from eta 1 to eta n minus 1, you get the same result as take the product between S1 and Sn. So then let's take a short break. When we come back, we'll continue calculating the partition function for periodic boundary conditions and for Ising chain. Okay, so let's take a short break. Continue calculating partition function for Ising spin in one-dimensional chain with the periodic boundary condition. And let's just plug in all this Ising interaction into the partition function inside of the summation, the product of the summation over all these eta variables. And then we can see from this exponent inside the summation, the Boltzmann weight, that depends only on all these etas from, say, eta 1 to eta n minus 1. It doesn't depend on this eta 0, but we still need to sum over eta 0. for the same reason that we sum over this spin 1 for this boundary condition that we just did. Okay, so there's a factor of 2 coming from sum over eta 0, but still we have the product of all this summation over eta 1 to eta n minus 1, but then we could just Taylor expand the last term, which is the product of all these etas from 1 to n minus 1, in terms of the Taylor expanded series of this k times eta 1 up to eta n minus 1 divided by alpha factorial, and this product is actually to the power of alpha. You sum over alpha from 0 to infinity. In other words, we Taylor expand exponential of k times this product of eta 1 to eta n minus 1 in terms of a power series of this product of all these different etas. But you can see very clearly that you could actually separate all the summation of individual etas from eta 1 to eta n minus 1 independently. You could actually single out all this summation over, say, eta 1, and you simply just take this e to the k times eta 1 and forget about all the other terms, and then you take this Taylor expansions expanded term, say only this eta 1 to the power of alpha divided by alpha factorial, and so on and so forth. You could consider all this in the product of the summation simply just a product of the same thing. Same thing meaning this summation over eta 1 is the same as summation over eta 2, and so on and so forth. And you simply just multiply all this n minus 1 kind of a single summation over a single eta. And as a result, you could simply just take the single summation as a basis, and you simply just put a power on each of the summation over a single eta, and this power is actually n minus 1 because there's n minus 1 single summation over eta, and multiply these n minus 1 summation together. All right? And therefore, you get this single summation over eta to the power of n minus 1, and you simply just copy all the remaining factors here, and you could again sum over this alpha from 0 to infinity, because this is simply just an easy task to actually sum over this alpha and sum over eta, and you obtain this slightly different form of a partition function, which is 2 times coach k to the power of n plus 2 times sinh k to the power of n. Okay, so I leave this to you as just not a homework problem, but just to verify this by yourself, that the summation over alpha and eta of that kind of a power series will indeed lead to that result. So you can compare this partition function for periodic boundary conditions, Ising chain or ring, to the partition function of a free boundary condition. And you can see that for a free boundary condition, you get 2 times 2 coach k to the power of n minus 1. But this periodic case, you get not only the coach, but also the sinh. And apart from this, the factor of 2 different, and also the exponent is slightly different. So let's just compare two forms of partition function with different boundary conditions and check what the effect of this boundary condition give us. And for the free boundary condition, we simply just take the minus kBt log of this partition function to get the free energy at finite size and fixed total number of particles and zero field, and you get this log stuff. And we can do the same thing for this periodic boundary condition, but let's just take a thermodynamic limit by taking the particle number to infinity for this free boundary condition. And if we do so, then this is actually cancelled. N minus 1 and n, in the limit of the large n, you get just 1. And at the leading order in n, you get this minus kBt n times log of 2 coach k plus a term which is order of 1 over n. When n goes to infinity, this is actually 0. All right, so if you take the free energy of a periodic boundary condition like this and take n goes to infinity, you get the same free energy, okay, as the free energy of the free boundary condition. So the answer to that question, the effect of the boundary condition, is that the effect the partition function, the free energy, at finite size, but it doesn't affect in the thermodynamic limit. Namely, in the thermodynamic limit, it doesn't matter the boundary condition that you impose, whether this is a free boundary condition or whether this is a periodic boundary condition. It doesn't matter. Okay, so this is good because it tells us that in the thermodynamic limit, it doesn't matter how you arrange your system, because when the system size goes to infinity, there are infinite number of particles or spins in your system. So it really doesn't matter what happened at the boundaries, okay, because the side on boundary is just two sides. Out of this almost infinite number of particles, the interactions at these boundaries doesn't play a role. And this is really a rigorous proof that boundary condition does play a role at finite size, but it doesn't play any role in the thermodynamic limit. So this is so much about the zero field Ising ferromagnet. So now let's turn to our attention to the partition function of an Ising chain when the field is turned on. So when the field is turned on, the calculation of partition function is not that easy or trivial as I just did, because you got the linear term in the field and the spins in the partition function. So we need to take care of that additional term in the summation. And that will lead to so-called the transfer matrix method. So the transfer matrix method is a very useful and powerful technique to analytically get this partition function of an Ising model and all other models that's similar to the Ising spins. Since we proved already that it doesn't matter which boundary condition that we impose at the beginning, so why not we simply just use the periodic boundary condition? So we will see later that this boundary condition is more convenient for us to get the analytical result. So now this partition function in the presence of field at the finite size is given by the trace of this Boltzmann weight. So as I mentioned, there is an additional term, which is a Zeeman coupling between the field and the local spin that appears in this case. But still, we could sort of separate this product of all this summation over all different individual spins in terms of a different product, a product of the different spins, summations. So we can actually single out and all the summation over individual spins and the Boltzmann weight associated with that summation. But we know that since the spins coupled nearest neighborly, and we cannot simply just single out the summation over a single spin, say S1. So the sum over this S1 also involves the sum over S2 because S1 and S2 are nearest neighbor sides. So then we could actually rewrite this partition function in terms of S1, S2, and S2, S3, and so on and so forth, and up to the very last term, which is the Sn and S1. Okay, so it seems that the summation inside the trace could be composed in terms of the product of the sum over nearest neighbor pairs. So these are all nearest neighbor pairs. So I'll stop here for today, and we'll continue next time to actually calculate the partition function of Ising chain in the presence of the field by using periodic boundary condition. And then we will define our transfer matrix next time. And we will get analytical form of a partition function of an Ising chain at the finite field. And then we analyze whether or not we have a phase transition at all for a one-dimensional Ising chain. And the answer is that we don't have any finite temperature phase transition in this case, and we only have a zero temperature phase transition. Okay? So, but we will rigorously derive such a conclusion next time.